All right. Our next speaker is Dr. Amena Ejaz Aziz. The topic is performance analysis of visible light communication for light modulation schemes. Amena Aziz received the BSc degree in 2004 from University of Engineering and Technology in Lahore, Pakistan. Sorry, that was her BSc, and PhD from Hong Kong Polytechnic University in 2019 in electronics engineering. Her areas of interest are visible light communication and signal processing. Currently, she is working as an assistant professor in the electrical engineering department of Institute of Space Technology, Islamabad. I believe one of Dr. Amina's students will be making the presentation if she would introduce herself as well. But Dr. Amena will be with us to answer a question. And you have 20 minutes starting now, so please go ahead.
Excuse me, sir. Actually, two of us will be giving the presentation, me alongside Ms. Sara.
All right.
Thank you, Professor.
Please inform us, what is your position? Are you students? Are you PhD students, master students, as you go along, please?
Yes. We are actually students doing our bachelor degrees from the Institute of Space Technology. Let us start with the presentation. Can you, is the screen visible?
It is now visible. Yes, please go ahead.
Assalamu alaikum and a very good day to you all. I, Aisha Qureshi, along with my group members, Dr. Amena Ejaz and Sara Shehzad, have been working on the performance analysis of visible light communication for white light modulation schemes. The aim of our research was to compare and analyze how various modulation schemes would affect the performance of a communication system. We have divided our work as shown in the presentation layout. We will start with a brief introduction followed by our methodology. We'll talk about the modulation schemes that we have implemented and then discuss our results and observations. Now coming to our
20 minutes, Aisha.
Yes.
Please go ahead. You have 20 minutes. Please go ahead.
Yes. Now coming towards the introduction, visible light communication is a relatively new and innovative technology in which information is converted into optical form and then propagated through the rapid flickering of LEDs. At the receiver side, a photodiode is used to detect an incoming optical signal and convert it into electrical form. Now, a question may arise is that we have already established wireless communication using radio frequencies. So why do we require VLC to assist RF? Well, we compared the two, and from our findings listed in a table below, we saw that for short working range, VLC is much more efficient in terms of power and bandwidth. Not only that, but if we continue to rely on RF as the only source of wireless communication, spectral saturation will become a very pressing issue. This was just a brief background. Now coming towards our actual research, before selecting a suitable modulation scheme, we have to look at several factors. First and foremost is power efficiency. Which modulation scheme provides the best SNR for a given bit error rate? Robustness to channel impairment. Which modulation scheme makes the signal most immune to noise and other channel effects? Which modulation scheme has the least cost and complexity of implementation? And lastly, spectral efficiency. Which modulation scheme requires the least bandwidth for transmission? Modulation schemes can be generalized into three main types: amplitude shift keying, phase shift keying, and frequency shift keying. For our research, we will be focusing on frequency shift keying, differential phase shift keying, which is a variant of PSK, and on-off shift keying, which is a variant of ASK. Now coming towards the methodology of our research, we performed our analysis through simulations using the OptiSystem software. For each modulation scheme, the performance of system was analyzed according to certain parameters: the FSO channel length, attenuation, power of transmitted signal, and data rate. So what we did was to select a parameter that we wanted to analyze, for example, channel length, and keeping all other conditions constant, we would perform a sweep analysis of over 20 iterations and observe the effect of that parameter on the overall performance of our communication system. The effect of each variable was judged on certain criteria. What we did was compare the received signal with the transmitted signal using visualizers. We would note bit error rate and quality factor. We would observe change in SNR, and we would observe eye patterns using eye diagram analyzer. All this data was collected by using the report feature of Opti system. So what we did was to observe the value of the input variable and certain output performance metrics such as minimum bit error rate, maximum SNR, and much more. All this data was collected, tabulated, and then graphs were plotted using MATLAB so that we were able to observe the trends much more clearly. Now, coming on to the simulation blocks, I would briefly describe them so that you are made more aware of their working when we move on to the schematics themselves. We defined the bit sequence using a user-defined bit sequence generator. This bit sequence was converted into pulses using an NRZ pulse generator and then converted into optical form using a white LED. The optical link was represented by an FSO channel. At the receiver side, a pin photodiode was used to detect the incoming optical signal and convert it into an electrical waveform. This electrical waveform was then passed through a low-pass bezel filter. For those of you who do not know, a bezel filter was used to generate group delay. After this, since we were passing the signal through a noisy channel, it had become weak and had noise introduced to it. So at this point, we introduced a 3R regenerator to regenerate that optical signal and reduce noise. Throughout our schematic, we made use of various visualizers and analyzers so that we could compare and analyze our outputs. For the two modulation schemes, DPSK and FSK, we used their respective modulators and a Mach-Zehnder modulator, which would calculate the phase difference between the incoming bit sequence and the carrier waveform and convert them into intensity modulation. Now, moving on to the first modulation scheme that we implemented, which was on-off shift keying. On the left-hand side, you can see the working of a theoretical on-off modulator, and on the right-hand side is the output we obtained for our schematic. Moving on towards the schematic itself, let me just, as you can see, this is our transmitter, which converts our electrical information into optical form. This optical data is transmitted using an FSO channel, and this is our receiver. We have used various analyzers and visualizers to compare our waveforms. The modulated waveforms that we obtained are as shown. As you can see, the received signal replicates the transmitted signal and verifies our OOK modulation. The only difference is that there's slight distortion in the amplitude of the received signal. Below the waveforms, you can observe the parameters that we have used. To ensure a fair analysis, we made sure to keep these parameters same for all three of our modulation schemes. The bit rate and the symbol rate were kept to 100 megahertz. The amplitude was 10 arbitrary units. The FSO channel length was 1 meter, and the channel attenuation was kept to 10,000 dB per kilometer. Now moving towards the next modulation scheme, differential phase shift keying. It is a type of phase modulation. On the left-hand side, you can observe the output that would be obtained from a DPSK modulation, and on the right-hand side is the output that we obtained from our schematic. Now, moving on to the schematic itself, the FSO channel and the receiver remain the same as that for a OOK system. At the transmitter side, there is a slight change. We made use of a DPSK modulator and a Mach-Zehnder modulator to obtain our modulated waveform. The output that we obtained is as shown. As you can see, that the received signal replicates the transmitted signal in terms of the time instances at which the sample is being taken. The only difference is that the received signal has a significant amount of distortion in its amplitude. As you can observe, the parameters have been kept the same as that for OOK. Now, moving on to the last modulation scheme that we implemented, here information was stored in frequency. Again, on the left-hand side, you can observe the working of an FSK modulator, and this is the output that we obtained from our modulator. Moving on to the schematic, this schematic was same as that for a DPSK modulator, the only difference being that here we use an FSK modulator. Other than that, the whole communication system was kept the same. Uh, the modulated waveforms that we obtained are as tuned. Again, here the received signal replicates the transmitted signal and verifies our FSK modulation. Uh, the only difference being that there is significant distortion in its amplitude. Now to discuss results and observations, I would like to call upon Ms. Sara.
Thank you, Aisha. I will continue on from here. Now, the first two parameters of range and attenuation, we judged the system performance in terms of minimum bit error rate and maximum quality factor. Generally speaking, an increase in the bit error rate and a decrease in the quality factor is an indication of poor system performance. Now, coming to the results, the first parameter that we varied was the range of the FSO channel. For double OK modulation scheme, it can be seen on the graphs that after a range of 3.5 meters, there's a significant increase in the bit error rate and a decrease in the quality factor of the system. For DPSK, we varied the range up to 8 meters. And as we can see, the bit error rate increases after 5.5 meters. Similarly, for the Q factor, at first this change is very slow, but then a rapid degradation is observed in the system. For our third scheme, frequency shift keying, this scheme displayed a very different behavior. Now, initially, the degradation in the system started right after 2 meters, but it was not prominent on the graph, and it was only prominent until 6 meters. Now, we plotted the bit error rate and the quality factor versus range graphs together for all three schemes. You can refer to the legend to see which plot line represents what modulation scheme. And now, comparing them all together, we found out that double OK starts to degrade at a very short range, whereas the other modulation schemes like DPSK and FSK, they take much longer before the system performance is affected. This means if you want to implement a double OK scheme, then the system range should not exceed 3.5 meters. And for the other two schemes, DPSK and FSK, they can be used for longer ranges. Now, ideally speaking, the lower the bit error rate and the higher the quality factor of a system, the better the system. Overall, double OK showed minimum bit error rate, which indicates good system performance, and FSK had the most bit error rate, which is a sign of a poor performance of system. So if you're looking for a modulation scheme that is based on a longer range, then DPSK just gives us the perfect compromise between the two schemes. The next parameter was attenuation. When we tested the first scheme for attenuation, a degradation was observed in the system after an attenuation of 36,000 dB per kilometers. This means that the double OK VLC system is capable of tolerating attenuation up to 36,000 dB per kilometers and works well within this range. We then swept the attenuation values for the DPSK system, and we used the same values as double OK. But we observed that this system starts to degrade rapidly only after 60,000 dB per kilometer. Then for the third scheme, in the case of FSK, although there's an increment in the bit error rate right after 36,000 dB value, just like in the case of range, this change is not visible until this change is very slow, and the rapid degradation is only observed after 60,000 dB value. Comparing the schemes together by sweeping them all over the same values of attenuation, we observe that double OK is more susceptible to channel noise, but has the lowest bit error rate for if the noise levels are kept within 36,000 dB. And hence, this modulation scheme is a more suitable option for VLC systems which have noise less than 36,000 dB per kilometer. As for the other two schemes, DPSK and FSK, while they both started to degrade at almost the same level of noise. However, the overall values of bit error rate of FSK were much higher than DPSK, which makes DPSK scheme a more suitable option for noisy channels. Coming to the third parameter, to judge the power efficiency of the modulation schemes, we analyzed the signal-to-noise ratio values of the received signal. This was done with respect to the parameters of channel attenuation as well as amplitude of the generated signal. For double OK scheme, we observed that at a very minimum level of attenuation, or at zero level of attenuation, the maximum SNR was under 100 dB. And it is completely degraded when the noise levels reach 36,000 dB of attenuation, which somewhat confirms our earlier results. Similarly, the minimum minimum value of amplitude, the SNR values are around 35 dB. For the next scheme, DPSK, the SNR value was much higher than double OK scheme at minimum noise level. It was around 120 dB. And the signal to noise ratio becomes worse with increasing attenuation. And for low amplitude, the signal also, this scheme displayed a better SNR value as compared to double OK. As for the third scheme, FSK, its SNR values were overall better than double OK, but they were still not as good as DPSK. Now, comparing the SNR values of all schemes together, we observed that the double OK has lowest SNR values, whereas DPSK has highest SNR values. And hence, DPSK, once again, it's a more suitable option for systems in which high SNR is a key requirement. For the last parameter, which was bit rate, now, in order to analyze the system performance with respect to the bit rate, we observed the eye diagrams for all schemes using eye analyzer. And we observed them at 4 different bit rates ranging from 100 megabits per second to 400 megabits per second. As for the rest of the parameters like range and attenuation, all those were kept at default values. Yes. Now, we observed that for the double OK scheme, it showed us an almost perfect eye diagram at 100 megabits per second. The eye height is maximum for this value, which indicates that there is minimum intersymbol interference and noise present in the received signal. And as the bit rate is increased, the eye height also decreases and a significant reduction in the quality factor is observed. For the second scheme, DPSK, the quality factor is overall less than that of double OK. And moreover, with increasing bit rate, it was observed that the system degrades speedily. And just as it reaches 300 megabits per second, the eye height becomes negative. So this system is less efficient at higher bit rates compared to double OK. For the third scheme, FSK displayed the lowest levels of quality factor, and however, it did have better eye height results than DPSK. Now, from our research, we were able to draw the following conclusions. First of all, comparing the schematics that were shown earlier for the different schemes, we see that double OK has the simplest circuit implementation. Furthermore, we conclude that as double OK displayed better eye diagrams for increasing bit rate with maximum Q factors and minimum bit error rate, on the other hand, at a higher bitrate, DPSK has the minimum eye height, which represents maximum interference in signal. This shows us that a double OK scheme is a better alternative for high bit transmissions, and DPSK cannot and should not be used for systems where high data rate is a matter of concern. Moving on, we found out that the optimum working range for each system is different. Double OK can perform best within the range of 0 to 3.5 meters. DPSK works well up to 6 meters, whereas FSK can work well till 5 meters. And DPSK and FSK can give a better performance for longer range channels. And to conclude, if a VLC system is based on short channel range, then double OK is a more suitable option. And adding to that, its implementation is simple and easy and as well as cost effective. On the other hand, for longer channels, DPSK has less bit error rate than FSK and requires less bandwidth for long range transmissions. Hence, the DPSK is found to be a better alternative. And similarly, for systems which have high SNR as a key requirement, this DPSK is a more viable option. In the end, we would like to thank the Arab ICT committee for allowing us to partake in this learning experience. Thank you very much. That's all from our side. If anyone has any questions, you may ask.
Thank you, Aisha and Zara, for a really thorough analysis of the problem at hand, and really an excellent methodology and very good testing procedures that you have done. I have a question from Dr. Ahmed Al-Wahoush. He's asking whether VLC suffers from echo problem and how you solve that. Maybe any of you can pick up the answer, please. You are muted.
Aisha, you're on mute.
Who's going to answer?
Miss Aisha.
Yeah, okay, Aisha, please go ahead.
Can they define what they mean by echo? Do they mean reflection and refraction?
Well, let's say let's assume that's what they mean.
We actually, for our analysis, we implemented a line of sight VLC system and we did not consider any reflection and refraction. Since we were focusing mainly on modulation schemes, we wanted to keep the system itself
Sorry,
as
Dr.
simple
Osama, can
as
you repeat the
possible.
question? Because I think my network was unstable, so I could not hear.
Yes,
it was some
Dr.
related to something with echo, I
yes,
guess.
Amina. Yes, Dr. Amina, Dr. Ahmed Al-Wahoush is asking whether VLC suffers from echo problem and how you can solve those. Did you hear me?
Okay. These two, Aisha Zara may not be able to answer this question because they did not handle this issue, implementation of echo or its what
Do you have
or to, I
an
mean,
idea whether there
they
will
did not
be
handle this
echo issue?
issue in this. Echo, I'm not sure what does he mean by echo because in visible light communication, the data is communicated through intensity of light, right? So there is ambient light or light the frequency is uh, not turnable or it's not as it is done in RF.
Sir, you're on mute, Dr. Sama.
Yeah, thank you, Dr. Amina. Yeah, we all suffer from this mute thing. Thank you, Dr. Amina. I understand from what you've said that there will be very limited echo problems associated with using VLC. Now, has VLC been used in any commercial product so far, or is it still under research?
Yeah.
Dr. Amina, we can't hear you, or maybe you can't hear us. Maybe Aisha or Zahra
Okay,
can answer.
I can see a question from Dr.
Yes, yes, I have seen
Samak.
the question from Dr. Abdul Imam As-Samak about
Correct.
the range of the system. The range of the system is very small. How to extend it for practical use?
Sir, I'd like to answer that question a little bit. To extend it for practical use, definitely we need to add more amplifiers. We can make use of amplifiers and add regenerators, etc. And that will help to increase the range of the system.
All right, great. And I asked whether VLC is starting to take over as a technology, or is it still in the research stage? Maybe
It's
one of you
it's
can answer.
Still in the
yes,
research
it's
stage.
it is still in the research stage, and the people are trying to make prototypes to implement it for practical use, but it's still a very new thing for the technological industry.
All right, great. Thank you very much, Dr. Amina, Aisha, Qureshi, Zahra, Shahzad. Really, we enjoyed thoroughly your presentation and very methodical testing procedure. So thank you very much. And you were on time, and now we can move to